Here is a question this series has been stepping around from the start. We keep saying a solution. Watch what happens when I draw not one solution to our equation, but many, each from a different height on the left edge. The plane fills with curves. Every one of them follows the arrows perfectly. Every one of them is a legitimate solution. One equation and an infinite family of answers.
Then when someone says solve the equation, which of these do they mean?
On its own, the question has no answer, and that is not a defect. The equation only knows the rule of change. It cannot know where your particular system began. The rule is the same for every pendulum in the world. What separates yours from mine is where it started. That extra fact has a name, the initial condition. So pin the start. Declare that at time 0, the system sits exactly here. Watch the family respond. Every curve that misses your point fades away, and the single curve passing through it lights up. An equation plus an initial condition is called an initial value problem, and unlike the bare equation, it has exactly one answer. And notice, this is precisely what our stepper from last time was always doing. Euler and Runge-Kutta never asked for the whole family. They asked, where am I now? The initial condition is the answer. It is the first foothold, and every step climbs forward from it. Pin a different start, and the same machinery walks a different curve. The rule of change, plus one fact about one moment, determines the entire future of the path. In the phase plane, the family is even easier to see, because we have been looking at it all along. For the spring, the family of solutions is the nest of ellipses from episode 1. Pinning the start means choosing a position and a velocity at time 0, which is choosing one point of the plane. One point, one ellipse through it, one motion forever after. Release the mass further out, and you have simply pinned a bigger loop. The pendulum's family is the full portrait. Swinging loops inside the eye, wrap around curves beyond it, and they fill the plane completely. Through every single point, there passes exactly one trajectory.
So the initial condition does not just pick a curve, it picks the kind of motion.
Beautifully put. Start inside the eye and you have chosen swinging. Start above it with enough speed and you have chosen spinning. Same rule, one pinned moment, and the whole character of the motion follows. One piece of honest fine print. I promise that pinning the start leaves exactly one survivor, and for the equations in this series, that promise holds. But it is not free. Here is a rigged equation, whose arrows flatten out too, gently near the horizontal axis. A solution can rest on that axis for as long as it likes, and then peel away upward whenever it chooses. Watch. Every one of these curves passes through the very same starting point, and every one of them is a legitimate solution. The promise needs the equation to be nice. The technical name, for those who want it, is Lipschitz. And every equation in this series passes that test. So this is where the series stands. Pictures show every motion the rule allows. The initial condition picks out yours, and the stepper walks it into the future. But some questions refuse to hand you the start. A ball must leave my hand now and arrive at the target in exactly 2 seconds. I know the beginning, I know the end. What I do not know is how to launch. That is a boundary value problem, and solving it is next. We aim, we miss, we correct.